Welcome to Lecture 3 for Chem 418 Nuclear Chemistry. This lecture is on radioactive decay kinetics. The readings for the discussion on radioactive decay kinetics are provided here. Modern Nuclear Chemistry, Chapters 3 and 17.7. Nuclear and Radiochemistry, Chapters 4 and 5. The basic radioactive decay kinetics will be explored, the concepts used in the equations, the uncertainty related to the data, and the relationship between an isotope lifetime and half-life will be introduced. There will be the utilizations of these equations in mixtures of radioisotopes, equilibrium systems, and we'll explore that there are two types of equilibrium, transient and secular, and then branching of radioactive isotopes will be explored and discussed. This occurs when an isotope can decay by more than one route. We'll also learn how to utilize the equations for dating of objects based upon naturally occurring radioisotopes. This figure here shows Schrodinger's cat, which relies upon a cesium atom, in which when it decays, it shatters the ampule poison and the cat dies. This is related to the probabilistic nature of a decay. We're going to see that for a given atom, we can't predict when a decay will occur, but we can talk about the probability of it decaying. And that probability relates to what we already know about the half-life, where we can discuss for a group of atoms the number that will likely remain after a given period of time, but we can't say whether for a specific atom that atom will survive a given period of time or not. We can only discuss radioactive decay in terms of probability.
DNA and career chip, please.
Erwin Schrödinger, huh? What's in the box, Schrödinger?
A cat, some poison, and a cesium atom.
The cat, is it alive or dead? Alive or dead?
Answer here, fool.
It's a superposition of both states until you open it and collapse the wave function.
Says you.
There's also a lot of drugs in there.
As an introduction to radioactive decay, let's talk about some of the basic concepts. The number of radioactive nuclei that decay in a radioactive sample decreases with time. So over time, we start off with the number of radioactive nuclei. As they decay, well, they may decay to other radioactive nuclei, but eventually there is a change from something that's radioactive to non-radioactive. And for a given decay, where let's say a radioactive isotope decays from something radioactive to something non-radioactive, we see an exponential decrease, that first law relationship that we saw on the previous slides. We also see that this radioactive decay is independent of pressure, temperature, mass action, and its first order. So in other words, the conditions are pretty well defined. Unlike something like chemical kinetics, this decay kinetics is really a first order decay. So there are some differences in terms of electron capture, internal conversion. So for instance, if I have an isotope that decays by electron capture, but there are no electrons on that isotope to capture, it won't decay through that route. The route still exists, it's just that there's no probability of that decay because there's no electrons. When is this relevant? If you're looking at cosmic rays, which could be described as particles, so flying through space, you could have a cosmic ray that's really just an atom accelerated so fast there are no electrons on this. And as a graduate student, I actually looked at this in terms of an isotope of niobium, understanding what was its, if it wasn't decaying by electron capture, what was its positron decay route. And that positron decay route is a much longer half-life than the electron capture. So something else that's about radioactive decay, it's specific for an isotope and it's irreversible. So in a lot of respects, different than chemistry. So an isotope, when it decays, that decay rate, that decay constant, which we show here and we discussed earlier, is consistent. And you don't get a reaction where something will decay by alpha and maybe it goes backwards where it absorbs that alpha. So naturally, you get all these terms. Radioactive decay is pretty specific. Now, the decay of a given radionuclide is random. If I had 100 atoms, just trying to select which atom that was radioactive would decay, that's probabilistic. I could make a bet that within a certain half-life, right, 50% would decay within the half-life, but I couldn't predict which one would decay. Now I could talk about the lifetime of each given atom, but I can't specifically state which radioactive isotope would decay at a given time. The decay rate is proportional to the amount of the parent isotope, so the decay rate is equal to the decay constant times the radioactive nuclei. So in other words, the counts per second, this decay constant times the number of atoms. So your activity decreases, since this is a constant, this is my activity decreases as the number of my radioactive isotopes decrease. Decay constant is average decay probability per nucleus for a given time. And that's what our decay constant is, log 2 divided by half-life, and we've discussed how to do these calculations in a previous lecture. The next few slides are going to discuss how some of the fundamental equations used in exploring radioactive decay are developed. This will allow us to derive the number of radioactive atoms that are present after a given time to account for decay. The probability for disintegration for any sort of radioactive atom in a given time interval is independent of its past and present circumstances. We describe this in terms of the conditions that its decay is fundamentally condition independent. So the probability of disintegration, it really only depends upon the length of your time interval that you're talking about. If it's a time interval is a half-life, the probability of a disintegration is 50%. So the probability of decay here is equal to the decay constant times whatever time interval we're looking at. The probability of it not decaying, well, it's 1 minus that p, right? So 1 minus the decay constant times the time interval. So the probability that an atom will survive n intervals of this delta t. We take this, we expand that equation, 1 minus lambda times delta t to the n, and then we get n delta t, well, that's just equal to our time, right? That's the number of this time units that we're interested in. That's our total time. Therefore, 1 minus lambda times delta t to the n is just equal to 1 minus lambda t divided by n to the n. Again, so that's n is the number of intervals, and t is this time. Let's take the limit as n goes to infinity. It's 1 plus x divided by n to the nth. And that's just e to the x. If we have 1 minus lambda t divided by n to the nth, well, that equals e to the minus lambda t. This is our limiting value. So this is how we derive the equation, one of the fundamental equation, to talk about radioactive decay. So if we have n initial atoms, we want to know the fraction that's unchanged in time t. We've seen this equation before, where n is the number of atoms remaining at time t. So n divided by n naught is equal to e to the minus lambda t. So we have this important equation that we've already presented. Now we've derived it, where the number of initial atoms times e to the minus lambda t is equal to the number of atoms at times t. Now this could be used for moles, it could be used for mass, it can even be used for activity, since we know that activity equals lambda n. So we could substitute activity for this term, n, in this equation. For counts arising from the decay of radioactive material, those are the counts that are detected by a radiation detector, there is an inherent uncertainty associated with the value. This is an important term to understand because it helps one design experiments in the laboratory based upon the need for data collection and activity of nuclides in experimental solids and solutions. In a radioactive decay process, as we discussed, the decay of a given isotope is random. So the number of atoms in a given sample that will decay can be different for a given time based on the uncertainty associated with the decay process. One can model this with the binomial distribution for radioactive disintegrations, in which case isotope is either decayed or it is not. This probability of an isotope decaying can be thought of as a coin flip in the time interval measured. As you would know,
a coin flip is 50% either side. However, each individual case is independent, and for a given set of coin flips, the 50% probability may not be reached. Radioactive decay is similar. It turns out that the uncertainty is based upon the number of counts that are observed. I want to emphasize that this is counts observed, not the decays. So for instance, if you have an isotope that has 100 decays per second, but your detector can only observe 10% of the decays, well, then you're only going to see 10 counts per second. So the counts are observed, and detectors have a range of efficiencies. And the term for the uncertainty is based upon this expanded equation, but in practice, the decay constant times the time is small. This value becomes 1, and the standard deviation winds up being the square root of the number of counts that one observes. The relative error from this effort is just the inverse of that value. An example is shown here where you have the counts, the uncertainty, and the percent error. You can see a collection of 10 total counts would have an uncertainty of 3.6. So you'd have 10 plus or minus 3.6 counts that you expect to have within a given sample. And the error is 31%. If you're going to use this value for determining a concentration, for instance, from activity equals lambda n, where you can determine the number of atoms of a radioactive isotope in an experimental sample, 31% error is not very acceptable. Increase the counts to 100, the error drops to 10. 1,000, 3.16, and 10,000, 1%. Normally, in the laboratory, having counts between 1,000 and 10,000 provides suitable uncertainty in your data and is within the general experimental error of other devices and apparatus that you would use in the laboratory. Generally speaking, the more counts you have, the lower your error. But as you can see from this table, 1,000 to 10,000 counts is reasonable error value. Anything over 10,000 counts, you'll be under 1% error, but chances are most of the procedures you'll use in the lab will exceed that error.
Let's discuss the relationship between activity and counts. When something decays, we discuss the activity of an isotope. It's got, activity equals lambda n. It may have an activity of 10 becquerel. So the question is, if I put that on the detector and I get 10 decays per second, how many of those are going to turn into counts? Because not every decay is observed. The detector is not 100% efficient. So we need to be able to convert counts to decay. For a given detector, its efficiency at detecting the radioactive decay can be determined, and that value is used to convert experimental count rate data to decay rate data. For calculating the activity, the fundamental equations can be used. Activity equals lambda n. Activity initial times e to the minus lambda t is equal to activity at a given time. So we have these relationships. And what we really need to do is when we talk about the relationship between counts and activity, it's the detector efficiency. The general relationships that one could see are shown here. If we looked at activity as a function of time on a linear scale, we'd get this relationship, the log scale, so a semi-log graph, we get a nice relationship. And the units for activity, I already mentioned becquerel, 1 decay per second. Another unit is the Curie, which is 3.7 times 10 to the 10th decays per second. This is based upon 1 gram of radium-226. 1 gram of radium-226. If I calculated the number of atoms in a gram of radium-226, so 1 divided by 226 times a mole, times the decay constant, which is log 2 divided by the half-life of radium-226, which is 1,600 years. That half-life does need to be converted into seconds. I get an activity of 3.7 times 10 to the 10th decays per second. So a Curie, that unit, is based upon 1 gram of radium-226. Details of this calculation are shown here. For the decay constant, log 2 is divided by the half-life in years, 1,600. There's 365.24 days in a year, 24 hours in a day, 3,600 seconds in an hour. That gives a decay constant of 1.37 times 10 to the minus 11 inverse seconds. The number of atoms of radium-226 in a gram is shown here, where the atomic mass of radium-226 is used, 1 divided by 226 times Avogadro's number, 6.02 times 10 to the 23rd, gives 2.66 times 10 to the 21st atoms of radium-226 in a gram of radium-226. These terms are then used to determine the activity by multiplying the decay constant times the number of atoms. So there are two activity units that are used, the becquerel, decay per second, and the Curie, this 3.7 times 10 to the 10th, decays per second. The equations that we've discussed can be used to help define some of the terms that we're already using. We've already discussed half-life. That's the time it takes for half of something to decay away. We've seen a few of these curves, the relationship if it's log or linear. The half-life, let's define it, it needs to decrease radionuclides by 50%. And there's a relationship between the half-life and the decay constant. If I took the general equation where the number of atoms at a given time t is equal to the number of atoms initial times e to the minus lambda t, I just looked at the ratio. So the time that it takes to get to a half is equal to e to the minus lambda t. So half is equal to e to the minus lambda t. Let's take the natural log of 1/2 is equal to minus lambda times the half-life, because that's the amount of time it takes for this relationship to occur. So, in 1 half-life, this ratio should be 0.5. And then log 2 is equal to lambda times the half-life. And the half-life is equal to log 2 divided by lambda, or lambda is equal to log 2 divided by the half-life, as we already defined. There can be large variations in half-lives for different isotopes. Short half-lives can be effectively measured. Imagine if I had something that had a half-life on the order of many minutes to hours. I could use a detector. I could sit and count the decay of that isotope if it was, 10 minutes, and I measured a sample every 30 seconds. If I measured the decay every 30 seconds, and I bin that, I could plot it on a line like I would have here, and I would get a decay constant. So something that's a short half-life, that's observable experimentally somewhere along this line, all I need to do is get some areas where I can get some change, some statistically significant changes, and I can generate the equation to derive the half-life. If it's a long half-life, and basically the rate isn't going to change over my measurement period, so imagine something with 10,000, 100,000 years, something like on the order of plutonium-239, around 20,000 years. This is based on the decay rate in the sample, so I need to know the total amount of a nuclide in the sample. So if I had some plutonium-239 and I weighed it, and I got N, and I got the activity of that N, well, I could solve for the decay constant, and then when I get the decay constant, I know that the decay constant is equal to log 2 divided by the half-life. I've measured the half-life. An example of doing something like this is with using a potassium salt. You could get potassium chloride. Potassium-40 is a naturally occurring radioactive isotope. One could put that on a gamma detector, look for the potassium-40, understand the efficiency of that potassium-40 peak on that detector in that geometry, and use that weighing the total amount of potassium chloride, knowing the fraction of potassium chloride that's potassium-40, calculate what the half-life is, and you can compare it to the measured value. So as opposed to discussing the half-life of a radionuclide, the amount of time it takes for half of that radionuclide to decay, I can also discuss an average lifetime of a radionuclide. So it's the sum of times of the existence of all atoms divided by the initial number of nuclides. So this average lifetime is equal to this equation here. And I can expand on this. It turns out to be 1 over the decay constant. 1 over the decay constant is equal to 1 over log 2 divided by the half-life. And it turns out that the average isotope has has a lifetime on the order of 1.4 times the half-life. So the average lifetime is greater than half the half-life by this factor. And during some sort of time of initial activity, it's reduced to 1 over E of its initial activity. So I can understand the relationships between these two. But when would you want to know the average lifetime? Well, a lot of times it's important if I'm talking about dose, if I want to understand what's going to be the average dose that one would get. You're talking about then you would talk about the average lifetime. Or if I'm doing atom at a time chemistry, which is what I did as a graduate student, if I only have one atom in a solution, half-life doesn't really make sense. And what you talk about is the average lifetime. So what we would do, we'd measure the average lifetime, get an ensemble of atoms together, measuring the average lifetimes, then we can get a half-life from that. But if you think about it, what you're really doing, if an ensemble, a regular experiment where I can measure the half-life, is really having a large enough collection of atoms to measure these individual averages in an ensembled system that allows you to derive something like a half-life as opposed to just a lifetime. This is a summary slide of everything we discussed previously. This slide has the equations one should focus on. We've got a few equations. This n at a given t is equal to n initial e to the minus lambda t, where this is some sort of number of radionuclides, the decay constant, and time. It also works for activity or counts, right? Because they're both related to n, the number of atoms. It could work for mass. It can work for anything that you could connect. If you could talk about a concentration, how the concentration changes, as long as the volume remains the same, but you're decreasing the number of atoms. We also have activity equals lambda n. So the number of atoms times n is equal to activity. So this is becquerel, which is counts per second, and curies, which is 3.7 times 10 to the 10th decays per second. So 3.7 times 10 to the 10th becquerels. We also have lifetime, which is the average lifetime of an atom is 1.443 times its half-life. And if you think about it from the decay, half the atoms should decay within the 1 half-life, but within 2 half-lives, 25% should be there. So the average atom is going to live a little bit longer than the half-life. And then finally, the error, where we have m is the number of counts, and this standard deviation is just equal to the square root of the number of counts. And we use this to determine how long we should perform an experiment to get a reasonable count rate so that the error generated from the counts isn't exceeding or driving the experimental error. Let's make some examples with these equations. So a half-life calculation, let's use the number of atoms at a given time is equal to the number initial e to the minus lambda t. All right, so we'll utilize this in terms of activity. We have an initial count rate of 890 becquerel. After 180 minutes, the count rate was found to be 750 becquerel. What's the half-life of the isotope? Well, activity at given time is equal to activity initial e to the minus lambda t. Solve for lambda. We get to lambda, and it's in minutes because we're looking at minutes. We get a value, this value here is equal to 9.5 times 10 to the minus 4 minutes, inverse minutes is equal to lambda log 2, which is equal to log 2 divided by the half-life. So the half-life is equal to log 2 divided by this value. So the half-life is equal to 729.6 minutes. I could also ask you, okay, how would you describe the error in this study? Well, you need some information. If the counts if the count was 750 becquerel, well, you need to say how long was it counted and what was the efficiency of the detector. Ideally, you'd like to go somewhere between 1,000 and 10,000 counts. The previous example showed an example of calculating a short-lived isotope, something where you can look at change over a reasonable time. Well, let's take an example of something where the half-life is rather long. So we use activity equal lambda n, and the example is 150 milligrams, so 0.15 grams of curium-248, shown to have an alpha activity listed here, 0.636 millicuries. So what's the half-life? First of all, let's find the activity. I'm giving you the activity in millicuries. You'd like it to put into something like counts per second. So 0.636 times 10 to the minus 3 curies times 3.7 times 10 to the 10th counts or becquerels per curie, counts per second per curie, gives me my activity in counts per second. So 2.57 times 10 to the 7th becquerel. I need to find n. That's pretty straightforward. If I give you the mass and you have if I give you the mass and I know what the molecular weight is from curium-248, I have Avogadro's number. I can get the number of atoms, which is shown here. And now I set up my equation. And I use the activity equals lambda n, solve for lambda. Put this in, I get lambda is equal to 6.46 times 10 to the minus 14th inverse seconds. Solve for the half-life, where lambda is equal to log 2 divided by the half-life. I get this equation, and I get my time unit in seconds because it's inverse seconds. So that is the one thing you need to be aware of, is that you got to keep your time units consistent whenever you do these calculations. Now the time unit in seconds, that's not really helpful. 1 times 10 to the 13th seconds. So we convert that to minutes, hours, days, years. So the half-life of curium-248 is 3.4 times 10 to the 5th years. We can use, again, activity equals lambda n from an example where we actually do some counting. Let's say you've got a gamma detector, and at 60 keV, the efficiency is 15.5%. What is the expected gamma counts from 75 micromoles of americium-241? Well, I use this information here to get the gamma branch, which is for americium-241.
The gamma efficiency data shown here is from the table of the isotopes and the Lund University site. These data sets include information not only on gamma decay, but other decay routes, and we will describe these data sets in more detail later in the course.
The gamma branch at 60 keV, so 59 right over here, is, I multiply it by 1 times 10 to the minus 5. This is 3.56 times 10 to the 6, so it's 35.9% is my gamma branch.
Unlike the table of the isotope data, the gamma branching values from the Lund University website are already normalized, so the value here is 35.9, which is the same value from the table of the isotopes.
So I need to take my detector efficiency,
which in this example is measured to be 15.5%.
Multiply it by the gamma branching. So in other words, for every time americium decays, 35.9% of the time this photon appears. When that photon appears, I only see it in the detector 15.5% of the time. Then I use my lambda n. That's equal to my counts. I put in my half-life.
Using the half-life of 432.7 years and normalizing that to seconds, where there's 3.16 times 10 to the 7th seconds per year, you get a half-life of 1.37 times 10 to the 10th seconds.
I get the seconds because remember I said the half-life needs to be at the same unit. It's given to you in years. I need to convert it to seconds. I use this seconds half-life to get the decay constant. So I want to find N. I tell you that there's 75 micromoles of the americium. It tells you how many atoms of americium are present. So activity equals lambda N, right? Which is this term. Then I still need to multiply it by the gamma efficiency and then the detector efficiency. So activity equals lambda N times the gamma branching ratio times the detector efficiency. But if I put this sample in, I would expect to have 1.3 times 10 to the 8th count per seconds. That's way too many counts. You would saturate your detector. So what this tells you right away is that that concentration is way too high. We're talking orders of magnitude. You'd better go to 75 nanomoles or even picomoles. You can afford to have 1.28 times 10 to the second counts per second. So you have a lot of variability that you can build into the system. Also helps you understand what concentrations are suitable for doing measurements in your experiments. Another term that's often used in radiochemistry is specific activity. And this is the activity of a given amount of radionuclide. So suppose you use activity equals lambda N, but it really defines how much of a mass or a concentration or a given amount of a radionuclide gives off a certain activity. So the specific activity is listed here, SA of radium-226. We've already described that. So 1 gram of radium-226, the half-life here, we go through the calculation, is equal to 3.7 times 10 to the 10th becquerels. Everything is listed here. And this is the definition of a Curie. This shows the calculations that are done to demonstrate that radium-226 is indeed a Curie. And this is an example of a specific activity where a gram of radium is equal to 3.7 times 10 to the 10th becquerels. And you can imagine doing this for a gram of any isotope you're interested in. So a final example of a calculation from the equations that we've covered in part 1 of this lecture is the lifetime. And let's look at an example of atom at a time chemistry, Rutherfordium-261. What's the lifetime of this atom? Half-life is around 65 seconds. So 65 times 1.44 is 93 seconds. And this we use to determine the time for an experiment. We would want to perform a separation and get that sample on the detector within 90 seconds so that that would be the same. So you're doing an experiment in the average lifetime of one of the atoms you're producing. So this gives you an idea if you're making short-lived isotopes, so elements that are on the edge of the periodic table and on the end of the heavy elements, which are short-lived, gives you an idea of how much time you need to prepare these samples and perform your entire experiment so that you're not having too many atoms decay as you're preparing the sample. At the end of part 1 of this lecture, we went over some equations. Some of those examples included the decay of a single isotope. Now we're going to start this lecture talking about the decay of a mixture of isotopes. So let's talk about a composite decay where we have 2 unrelated isotopes. So the sum of all the decays are just thought of as the mixture of the 2 isotopes. So the 2 isotopes are acting independently. So the 2 radioactive species are mixed together. We can count the total activity as a function of time. Here's an example of what a curve might look like, and you can see that it's composed of 2 isotopes. So we can say that activity at any given time t is just equal to the activity of isotope 1 and the activity of isotope 2. That's equal to the decay constant of 1 times the number of atoms of 1 plus the decay constant of 2 times the number of atoms of 2. We can rearrange this equation where we have the activity at any time t is equal to the activity initial of isotope 1 times e to the minus lambda t, where lambda is the lambda for isotope 1, plus the initial activity of isotope 2 times e to the minus lambda 2 times t. We can take this equation and then solve this line for this equation. So we take this equation, put it into a solving program, generate the equation of the line, which is shown here. And then we also determine the terms of the components of this equation. So t is the x-axis, so we'll be able to solve for a1 naught, a2 naught, and lambda 1 and lambda 2. We run the equation. In this case, we solve for lambda 1 and lambda 2. These values are shown here. So the lambda is provided. We can get the half-life. We can get the initial activity of isotope 2, and then the decay constant for isotope 1, the half-life of isotope 1, and the initial activity of isotope 1. We can also solve this graphically if we examine two parts. This is the longer-lived isotope. At the longer times, its decay dominates. You linearize on this semi-log figure. The longer-lived terms go back to the origin. You get around 2,000. So if I look at the value, 2,000 minus the total value would be equal to the shorter-lived isotope. So you could solve this graphically, or more directly, you can solve it by just solving for the equation of the line that was generated. Then we can expand these equations into related decays, in other words, a parent and progeny, daughter decay. So we know that we have conditions where one isotope decays into the other, the decay series being the most common examples. So here's a figure that shows the uranium-238 decay chain, also the 232 thorium, and then there's uranium-235 decay series. Those are the natural occurring decay series. However, you can pick out a number of isotopes that will often, particularly if they're far from the line of stability, they will also have decay chains. Example here, uranium-238 decays to thorium, eventually makes its way all the way down to stable lead-206. There are actually 4 series. One of them would start with neptunium-237, which is short enough lived compared to the lifetime of Earth and the solar system that it will have all decayed away. So for any system like this, for a parent-progeny decay, the rate of progeny formation is dependent upon the parent decay rate minus the progeny decay rate. And it's this relationship that we're going to really exploit to help understand the equations and how we can address under relationships between parent and progeny decays. Let's consider the case of a progeny isotope being produced from the decay of a parent isotope. So we have an isotope 1, and it decays into isotope 2. So the change of isotope 2 over a function of time is just equal to the decay of the parent producing a progeny isotope, and then any subsequent decay of that progeny isotope. We rearrange this equation. We get this term, we get this equation. So let's solve and substitute for N1 using N1 at times t is equal to N1 naught initial e to the minus lambda t. That equation then becomes what is seen here. Let's take a linear first order differential equation. Let's just solve by integrating the factors to solve this linear first order differential. Let's multiply by e to the minus lambda 2t. The equation then becomes what we see here, where we get the change of n2 e to the lambda 2t is equal to lambda 1, the initial amount of isotope 1 e to the lambda 2 minus lambda 1 t with respect to time. So we've gone through the equations. We now have this equation, which we further treat to reach our final equation. Now let's integrate over time. So let's provide the integral, and we get this term. So let's integrate over what we see here, lambda 1, n 1 naught e to the minus lambda 2 minus lambda 1 times t, divided by the difference between lambda 2 and lambda 1. From 0 to t, the equation becomes n2 e to the lambda 2 times t minus n2 initial is equal to a ratio of the decay constant for 1 divided by the difference between the decay constant for 2 minus 1 times this term n1 e to the lambda 2 minus lambda 1 times t minus 1. Multiply by e to the minus lambda 2 times t and solve for n2. Remember, we're talking about the progeny. So we're looking for n2. n2 at any time t is equal to the decay constant of the parent divided by the decay constant of the progeny minus the decay constant of the parent. This describes the relative growth and decay. So the decay of the parent is growing into the progeny, but as the progeny decays, it's disappearing. So you have the parent decay rate filling the progeny, and then the progeny decay rate having the progeny disappear. The initial amount of the parent times e to the minus lambda 1 times t minus e to the minus lambda 2 times t plus any amount of the progeny that is originally present. So let's consider that term also. So now we have this relationship where we can use to provide an understanding of how much progeny is present at a given time t based upon an initial amount of parent and even an initial amount of progeny. So we have part of the equation which describes the growth of the progeny from the parent and then initial amount of progeny. So pretty straightforward. We have these two components that provide information related to the amount of the progeny available at any given time. Now, since we found n, the number of atoms, we can solve this equation for determining the activity of the progeny at any time by using the relationship between the number of atoms and activity. So activity equals lambda n. So we multiply this by lambda 2. So we take the term. Again, we have an initial amount of the parent, and now we have the progeny term. We can use this to find maximum progeny activity based upon just change of the progeny with respect to time equal to 0. We're maximizing. And let's solve for t. We have the equation where the time that it takes to reach this maximum is equal to the natural log of the ratio of the decay constants divided by the difference of the decay constants. And that's not too surprising. We don't need to understand the amount of material that's available, parent or progeny, for it to reach a maximum amount of progeny. All it is a ratio and a difference of the decay constants of the parent and the progeny. We can use this equation, input data that says if I have a generator, for instance, I'm making technetium-99m, which is a 6-hour half-life from the decay of molybdenum-99, so this is the parent, this is the progeny. Find the time for the maximum progeny activity. Well, we just plug in the lambda 2, which is the technetium. Lambda 1 is the molybdenum. We make sure the units are the same, days and hours. So make sure you convert this hours into days. And this basically says in about a day, this has reached a maximum. And this is actually a useful consideration, useful term. Technetium-99m is a workhorse for radiopharmaceuticals. It's sent to medical centers as molybdenum-99 on a generator. That generator, the molybdenum decays into technetium-99m. Molybdenum is decaying with a 2.75 day half-life. Technetium is a half-life of 6 hours. So this basically says you can separate the technetium from the molybdenum, wait another day, and you'll have reached a maximum amount of technetium you're going to get from that generator. In the previous slide, we used a differential to evaluate conditions where maximum amount of progeny would be created from the decay of a parent. We can actually make some more simple relationships based upon the relative differences between the decay constant of the parent and the decay constant of the progeny, or the half-life relationships. So in other words, there are relationships where if the half-life of the parent is much longer than the half-life of the progeny, you can simplify some of the equations. So let's take a few conditions. For instance, the simplest one would be that there's no progeny decay. The number of progeny atoms is just due to the decay of the parent. Number of progeny atoms keep growing, and the parent value keeps decreasing. So this is where if I had an isotope that was decaying directly into a stable progeny, that would be the case. And let's say if the progeny is radioactive. There's a few different cases where there's no equilibrium. Equilibrium means that eventually relationship between the decay of the parent and the decay of the progeny be established. If the parent is shorter lived than the progeny, or if the decay constant of the parent is much larger than the progeny, no equilibrium is attained. Progeny obtains a maximum activity when this condition is solved. But imagine you have a condition where the parent has a half-life of a second and the progeny has a half-life of a year. So within 10 seconds, all the parents decay and all those atoms are now progeny atoms where its half-life is a year. So within a year, half those progeny atoms will have decayed. So initially, you'll get this burst of parent activity, then decay will be solely based upon the decay of the progeny. Another relationship is where the parent half-life is greater than the progeny half-life. And we'll see that there's actually two types of relationships that we can describe this way. One is transient equilibrium. In this case, where the parent half-life is about 10 times that of the progeny half-life. One of the other properties is that due to the relatively short parent half-life, the activity of the parent may change during the measurement time. So this is called transient equilibrium, so that there's a change that's ongoing. Now, the decay constant of the progeny is going to be greater than the decay constant of the parent. The ratio between the parent-progeny becomes constant over time. As we see, as shown here, here's a total activity. There's a activity of the parent. There's a progeny activity that grows in. That ratio becomes constant over time. Now, this ratio is going to be the same. The total value will change. So we see that this ratio is going to be constant. And as t goes to infinity, the activity goes towards zero. And we can collapse the equation so that the number of progeny atoms is approximately equal to the decay constant of the parent divided by the difference between the decay constant of the progeny and the decay constant of the parent times the initial amount of the parent, e to the minus lambda t, so the decay rate of the parent. It becomes this equation. And then we can just look at a ratio. The ratio between the number of progeny atoms and the number of parent atoms at equilibrium is equal to a ratio of the parent decay constant divided by the difference between the progeny and the parent decay constant. Now, imagine we have a condition where the parent is much, much longer lived than the progeny. Generally, what this means is that over an observed time frame, the parent activity doesn't change. So imagine you're measuring something that has a half-life of 1,000 years, 10,000 years, and you're measuring it for 100 hours. The amount of change that is going to occur in that parent will not be observable, but the progeny may grow in during the measurement time. So you may have an amount of parent, B shown here. The progeny grows in, and then the total activity is basically twice the parent activity. So in this case, the parent does not measurably decrease in many progeny half-lives. We see that that seems to be the case. And then we have this relationship from the transient equilibrium. And lambda 2 minus lambda 1. Lambda 1 is a very small number. It's fundamentally just equal to lambda 2. So we get these relationships where n, the number of progeny atoms, divided by the number of parent atoms is just equal to a ratio of the decay constants. And we actually see that what we get over time is that the activities of the two become constant. If I were to take this equation, n1 lambda 1 is equal to n2 lambda 2. So this equation, our transient equilibrium, since this value is small, we basically eliminate it from the equation for the secular equilibrium. And then we get these conditions, and the key condition being that the activity of the progeny winds up being equal to the activity of the parent. The equation that relates the time needed to achieve maximum progeny activity with the parent and progeny decay constants was already provided. As a matter of practice, the equilibrium between the parent activity and the progeny activity usually occurs between 7 to 10 times the progeny half-life. And there are details involved in actually measuring the activity and the uncertainties from the value, which is the reason why one would say that there's a range of half-lives. But as a reasonable rule of thumb, saying that the parent and progeny activities are equal within 7 to 10 half-lives of the progeny is accurate. Well, what if we have a condition of many decays? So parent, one progeny to the next, to the next. So here's an example of a decay chain that you could calculate with the Bateman equation. It's the decay of neptunium-237 going all the way to bismuth-209, and then they even show the decay of bismuth-209 to the thallium-205. As a note, this is somewhat controversial since most data sources show bismuth-209 as a stable isotope. Let's take the example of the second progeny, which would be indicated by N3, since N1 is the parent, N2 is the first progeny, N3 would be the second progeny, and so forth. So that's the change in the specified progeny with respect to time is just equal to the decay of the progeny 1 that is populating progeny 2 minus the decay of progeny 2. And we use the Bateman solution to calculate this entire chain. And the equation for the Bateman solution is shown here. It assumes that only parent is present at time 0, and we have a factor where this C1, C2, Cn factor, so whatever n is, the number of progeny to be calculated, it's equal to this factor here, which is shown as the decay constants from 1 to n minus 1, and the difference between the decay constants of 2 minus 1, of 3 minus 1, so of all of them for this subscript value, all the decay constants minus that value, time the initial amount of the parent. This C2 value, and again we've got C2 e to the minus lambda 2, so that's the progeny 1 decay constant. Well, that's just equal to, again, the same factors here, all the decay constants to n minus 1. So depending upon what your n value is here. And then the decay constant of 1 minus 2, decay constant of 3 minus 2. Now we've taken what we're subtracting the decay constant by is the coefficient or the factor of this C value. It goes on and on. So you can build many, many chains. As you can imagine, writing this yourself, there's a lot to take into account. Another way to do this is to get a Bateman solver. There's Bateman solvers available. One of these programs that solves isotope growth and decay will be presented and can be found at this website. Using the Bateman equations described previously, let's explore a decay and solve for the parent and progeny isotope number and activity as a function of time. We'll use the decay of lead-210, which is shown here. This isotope decays to bismuth-210 through beta decay, and that decays to polonium-210, again through beta decay, and the polonium-210 emits an alpha, and the progeny from that is stable lead-206. So in this decay, we have 3 radioactive isotopes and 1 stable. Let's evaluate the data from the chart of the nuclides and use that in the Bateman equation. We can list the decay mode just for convenience, but the important term is the half-life. So the half-lives of the isotopes in question are provided with their units, and they are the lead-210 half-life is 22.3 years, the bismuth-210 a little over 5 days, and polonium-210 about 140 days. Lead-206 is stable. So let's convert all the half-lives to the same unit and calculate the decay constants that we'll need in seconds. So here we have a table, and I just do this in Excel. I take the units, and then I write an equation in which I take the unit for the time and convert that into seconds. Log 2 divided by the seconds provides the decay constants for the isotopes of interest. And again, note that the lead-206 is stable. Continuing on, using the data we discussed, the Bateman equation can be set up and solved. So what one does is we need to solve for the lead-210 and its progeny based upon an initial amount of lead-210. So let's just do a quick schematic of the decay from lead-210, which we're going to define as N1, bismuth-210, N2, polonium-210, N3, and then the stable lead-206 is N4. We'll define N1 naught as the number of lead-210 atoms at time 0. From the parent and progeny isotopes, the number of atoms at time t can be found from these equations. For the lead-210, N1, at any given time t, it's just based upon the standard equation from the initial amount of lead-210. For the first progeny, bismuth-210, we use the equation that we derived for the simple parent-progeny equation. For the second progeny, polonium-210, N3, this is where we use the Bateman equation. We set up the Bateman terms based upon the initial number of parent and the decay constants for the parent, the first progeny, and the second progeny. For the lead-206, which is stable, we just take the amount of lead-206 from the difference of the initial amount of lead-210 atoms minus the amount of lead-210 atoms at time t plus the amount of bismuth-210 atoms at times t plus the amount of the polonium-210 atoms at time t. We don't need to account for the decay of the lead-206 because it is stable. We can set this up in Excel and calculate for the number of atoms of the parent and the progeny at any given time. And since we know the number of atoms, we can also calculate the activity by multiplying the number of atoms by the decay constant for that isotope. And here's an example of the data in an Excel spreadsheet where the first table is the isotope half-life converted to seconds with the decay constant. These are the terms that are then used along with the initial amount of the parent, in this case lead-210. The times, in this case, the times are selected in years and half-year units, and that time is converted to seconds. That's used within the Bateman equations and the decay relationships to determine the amount of a given atom as a function of time. And as you can see with this, the number of parent atoms decreases as we go down. Obviously, it's a 22-year half-life, and we're going from 0 to 10 years. And then we can see that the first progeny, the bismuth-210, increases and then reaches an equilibrium state where it's decaying because of the decay of the parent. And then same for the second progeny, and then finally an increase in the number of the stable lead-206. We could take this data, and since it's the number of atoms multiplied by the decay constants that we've derived here, and get the activity for each isotope as a function of time. Of course, the lead-206 would not have an activity as it is stable. And if we go to this website, you'll see a page. Click here to download the program. It'll ask you for some information, and then you can download the program. This version, there's also a link on the Canvas site, version 2002 available. You can read the information that's available. They are looking for feedback, so they'd be happy to have feedback. And this is a PC program, so it does not run on an Apple product. We'll use the other ERG program, version 2.002, which is copyright from 2012, to provide an example of just the decay of atoms as opposed to activity. So let's pick an isotope to start with. Let's select zirconium-95. So we select the element, then we select the isotope, zirconium-95, niobium-95, molybdenum-95, beta, 2 betas, and a stable molybdenum-95. The input data isn't done by clicking on this bar. It's done through the table. So let's just say there's 100 atoms of zirconium, fundamentally a percentage. And let's also include the molybdenum into the output since we're talking about atoms. Let's click on the parameters, pull up the parameters. Let's go for 200 days, shown here. The half-life is 64 days, 34 days, and stable. So we should see some growth and decay in this period. Select that. Let's calculate it. Here comes the graph. And sure enough, we see that zirconium decays, the niobium reaches a maximum, then starts to decay, and the molybdenum does nothing but increase since it's stable. We can select this bar. If I move this around, I get the day and the amount of the zirconium, niobium, molybdenum. I can see that the niobium, I can see where it kind of reaches a maximum, then where it starts going down, and I can quantify that. Just like the other program, I can evaluate the data. So here's an example of the amount of atoms as a function of time. Obviously, this value should be 0, but we go through and we can see that zirconium does nothing but decrease. Molybdenum goes up, reaches a maximum, then starts decreasing, and molybdenum just increases. It does not decay. And just like the other program, we can export the data. I can export it as a CSV file. There's also some data libraries. I can look at the emissions, the alpha. I can select an isotope alpha, beta, and the gamma emissions for the isotope. I can select niobium-95, look at its emissions, no alphas, 3 beta energies, 3 gamma energies. I get the energies and the decay probabilities. I can also look up atom, if I just have a gamma decay, I can write in, for instance, a gamma decay, 661.6 keV. I can do a tolerance of 0.1 keV, so it'll be 661.5 to 661.7. It pulls up all these values. So if I was interested in, if I just saw a gamma line, for instance, cesium-137, that's the gamma that I'm thinking of, I can get that gamma and also its decay probability. So this program, you could use this program, you can use the ERG 1.001. Either will work for looking at growth and decay, series, daughters, decay chains. You can get data out of both. If there's any assignments, these will be used on, they'll operate on PCs, they won't operate on Macintosh. And if you have an issue with that, we can resolve that through the course. One of the terms we discussed in the example of the uranium-238 decay is branching decay. And this showed a condition where an isotope will decay by 2 different routes. Alpha and beta was the example that was shown in that decay. Now, if you look up an isotope on the chart of the nuclides, you're only going to find 1 half-life. So an isotope only has 1 half-life, therefore it only has 1 decay constant. But actually what that decay constant is, it's fundamentally a sum of all the decay constants. However, often only one decay constant dominates. It's fundamentally equal to the observed decay constant, so that half-life is the observed half-life. If something has a very low probability, it has a large half-life, and it often isn't observed or difficult to observe. So for a branching ratio, you could actually calculate partial half-lives or partial decay constants. From this equation here, the sum of any decay constant is just equal to the sum of its components. And let's take an example of an isotope that decays by alpha and beta. So the alpha decay constant and the beta decay constant is equal to the total constant. The branching ratio is just the ratio of the decay constant of the alpha divided by the total decay constant. You could also look at the half-lives, where the branching ratio is the total half-life divided by the half-life of the decay route. So in this case, you'll observe that since it's a number less than 1, the half-life of the decay routes are less than the half-life that is provided than the observed half-life that's provided in the chart of the nuclides. So let's consider an example, bismuth 212. What's the half-life for each decay mode that decays by alpha and beta? We see that there's a 36% alpha branch, 64% beta branch. The decay constant's the half-life's about a minute. So log 2 divided by 60.55, the decay constant's about an hour. The half-life's about an hour. The decay constant is log 2 divided by 60.55 minutes. We see that the branching ratio is equal to, for the alpha 0.36, is equal to the alpha decay constant divided by the total decay constant. Let's solve for the alpha decay constant. As shown here, we get a decay constant of 0.0041 inverse minutes. Log 2 divided by the half-life is equal to the decay constant. We use that to calculate the alpha decay, which is about 170 minutes. The alpha decay half-life. We do the same thing for the beta decay. We see that its value is about 95 minutes. We could calculate the half-life directly using this ratio. If I know that the half-life total is 60 minutes, the alpha half-life is equal to the total half-life divided by the branching ratio. Same thing for the beta, total half-life divided by the branching ratio. So in this way, if you're given a total half-life and a partial decay constant or partial half-life, you could calculate the branching ratio, or you can calculate the decay constants and the half-lives from the branching ratio. Here's an example of the utility of the equations we've just explored. This figure shows the radiotoxicity of radioactive waste as a function of time, and you see the radiotoxicity is listed in sieverts per metric ton of natural uranium. It's a way of comparing the toxicity of spent fuel to that of natural uranium. So there's this line that shows natural uranium ore. So the idea is, how long would you need to wait so that spent fuel becomes as toxic as natural uranium? And you see this point over here. Now the dose, and when we learn about dose, we're going to see that it's related to activity. So all the equations, the growth and decay equations we discussed, can be applied to generating this figure. And we see that we're able to break the waste into different components. There's fission products, which are generally short-lived, and that dose decreases over time. There's minor actinides and decay products. There's plutonium and decay products. So this gives you an idea of what components of radioactive waste contribute to the dose. And this is important when we discuss separations in radioactive waste treatment and the nuclear fuel cycle. We also see here that this is for an average burnup of 50 gigawatt days per metric ton for a light water reactor. And those are conditions of a nuclear reactor that we will briefly touch upon in this course, and we may have a full lecture in it. So overall, the equations we discussed can derive data such as this over a period of 1,000,000 years, and in this case, the equations can be used to evaluate the radionuclide activity and dose over time. We now have an opportunity to take these equations to calculate growth and decay and use them to explore how we can determine the age of materials based upon naturally occurring radionuclides. So there are two sets of naturally occurring radionuclides, let's say primordial radionuclides, that have survived since they were first deposited on Earth. They tend to have a half-life of greater than 1 billion years. They also have decay products that are formed from these long-lived radionuclides. We saw the example of uranium-238, uranium-235, thorium-232 are also decay chains. And here's an example of potassium-40. And again, I wanted to point out from the chart of the nuclides, this black bar here designates that it's a naturally occurring radionuclide. In this case, long-lived. Potassium-40, any potassium-40 that was originally deposited on Earth 1 billion years ago has gone through on the order of 1 half-life. The age of the universe, nominally 4.5 billion years. The potassium-40 has gone through a half-life, but there's still a reasonable amount of material. Now, there's also shorter-lived radionuclides that are formed from continuous reactions with cosmic rays and with matter. So, for instance, tritium, carbon-14, beryllium-7. Here's the data from the chart of the nuclides for carbon-14. Its half-life is 5,000 years. Obviously, if any carbon-14 that was originally deposited on Earth during the formation 1 billion years ago is long since decayed. But these nuclear reactions, and for carbon-14, neutrons hitting nitrogen-14 produce a proton and carbon-14. And these reactions, there's also a reaction for producing carbon-12, but this reaction, as you can imagine, this is a neutron with sufficient energy to knock out a proton. This reaction occurs because the atmosphere is primarily nitrogen. Most of that is nitrogen-14, so this is our target. The neutrons are formed from cosmic rays coming in, forming these neutrons in nuclear reactions, and those neutrons then hitting the nitrogen-14, liberating a proton, and forming this carbon-14. Now, anthropogenic radionuclides have also been introduced, so radionuclides made by human activity. These are primarily actinides and fission products. They also include carbon-14 and tritium, and these have been introduced through weapons testing. All these radionuclides, particularly the naturally occurring ones, can be used to evaluate dating. However, if one is going to use carbon-14 or tritium, or anything that was introduced through anthropogenic activities, a normalization has to occur for accurate dating of these materials. So if we have a long-lived isotope that decays to some ground state or stable progeny or long-lived progeny, we can use this as a clock to determine the age of something. And the clock is basically from this equation where the number of atoms at a given time t is just equal to the number initial times e to the minus lambda t. So let's rearrange this equation and solve for t, and the equation becomes what is shown here, where it's equal to the natural log ratio of the initial and the number of atoms at time t, and the decay constant of what's decaying. This doesn't really seem to help because it implies that we need to know the number of atoms at time 0. I can measure at time t. If I know what isotope is decaying, I've got the decay constant, I just don't know this value. We need to be able to determine what this time t is, and what we can say is that, well, the decay of the parent to the progeny is constant. And let's just say the total amount of progeny plus the total amount of parent at time t is equal to the initial amount of parent. And all we're saying is that we can determine the amount of the parent, so this n naught value, based upon what we measure currently for the amount of progeny and the amount of parent present. For the nomenclature, we will use P for parent and D for the progeny. D, daughter in this case, but we'll state it as progeny, but for the progeny, the term will be D. We can start with the equation where the amount of parent at time t equals parent initial e to the minus lambda t. We use the conditions where there is no progeny present at time 0. All the progeny is due to the parent decay, and no progeny is lost during the time of decay, so this time t. We can rearrange this equation so that the progeny at time t is equal to the parent initial minus the parent at time t. This becomes the parent at time t times e to the lambda t minus 1. And then solving for t, we rearrange this equation to what is shown here, where t, the age of the sample, is equal to 1 over the decay constant times the log of the sum of 1 plus the ratio of the progeny atoms to the parent atoms. So let's consider how this could work. Imagine that there's a mineral, for instance, zircons, which are zirconium oxides, have a small amount of uranium embedded in them. One can evaluate these zircons, look at the amount of uranium-238, and the progeny we're talking about in this case is lead-206. Now, if you look at the decay chain, that's not a direct decay. There are many decays, but fundamentally, if you look at the half-lives of the isotopes between uranium-238 and lead-206, most of them are relatively short-lived compared to the half-life of uranium-238. So in essence, we just can take the uranium-238 half-life as a decay directly to lead-206. So what we need to assume is that there was no lead-206 present at time 0 in this zircon. All the lead-206 that is there is due to the decay of uranium-238, and that no lead-206 was lost during the lifetime of this material. What you could do for lead, if you were to evaluate if there was other lead present, lead has other stable isotopes, you could determine how much lead there is, look at, for instance, lead-208, how much of that was there. And if you don't see the lead-208, convinced that lead is only from this decay. Also, the isotopics of the lead will show you that information. Of course, if there's uranium-238 present in your sample, you're probably also going to have uranium-235, and those progeny will also need to be considered. So if we go through this, what is the age of the mineral? Let's substitute our terms into this equation. So it's the decay constant, which is log 2 divided by 4.5 billion years. The log of the sum of 1 plus the ratio of the progeny to the parent. And I said that the fraction is shown here, the ratio. So we can just take those values. At time 0, the progeny isotope lead-206 is not present. At time t, which is now, the progeny to parent ratio is 0.4. So this becomes the inverse of the decay constant times log of 1.4, and you get 2.2 billion years. That's a relatively consistent time frame for some zircons, and this technique is actually used for dating older zircons. Again, we use this equation. This is our fundamental equation. All we need to know is the decay constant and the ratio of the progeny and the parent today. Carbon-14 dating is a little bit different. This is based upon the uptake of carbon-14. So for carbon-14, the half-life is around 5,700 years. This is a good time to show some variation in literature data. There are 3 half-lives for carbon-14 shown here, 5,715 years from the chart of the nuclides, 5,730 years from the table of the isotopes, and 5,700 years from the Brookhaven website. The choice of the half-life will have an influence on the calculated age of the sample. So if one ever evaluates literature, you should make sure you explore and understand which reference was used for the carbon-14 half-life. For carbon-14 dating, the baseline is that an organism, as it's alive, is taking in carbon. The ratio of carbon-14 in natural carbon is constant, and it's due to the natural formation of carbon-14 in the environment. Dating with carbon-14 is based upon when the organism stops uptake of equilibrium carbon-14. That organism is no longer taking up carbon upon its death, or it ceases that interaction. So the carbon-14 begins to decay. If I know the amount of carbon-14 in a certain amount of carbon at equilibrium, so at time 0, and I see how much carbon-14 there is per a unit mass of carbon at the current time, one could measure the sample age. We just rearrange the equation we used previously. 1 divided by the decay constant of carbon-14 times the log of the carbon-14 at equilibrium divided by the carbon-14 in the sample. So the equilibrium value is listed here. And what's the age? There's a wooden sample that's been found. It now has 0.15 becquerel per gram. This is 227 becquerel per kilogram, so we need to make it per gram, so it's 0.227 becquerel per gram. Let's rearrange these equations, and we get the natural log of 0.227 divided by 0.15, and we get 3,420 years. So carbon-14, 5,000 year half-life, is reasonable for doing carbon dating on that order, so thousands of years. There's actually another way that you can do carbon dating as opposed to looking at the radioactive decay. You can use a mass spec and count the number of carbon-14 atoms in a carbon sample. So you get that ratio, right? The activity is fundamentally using activity equals lambda n. I can get the number of atoms of carbon-14 per the number of atoms of total carbon. If I use the mass spec, I can actually count them, and you can go to actually lower detection limits, and that's one of the methods that is used today. And again, it's the same equation that we talked about previously, but now it's specialized for normalization of carbon-14 at equilibrium. And the equilibrium value shown here, again, this is listed in becquerel per kilogram. If your data is provided in grams, you need to change that normalization. These dating equations can also be varied to evaluate some conditions to understand the age of certain objects. So for instance, we can use an example as the Oklo reactor. This is provided on page 40 on the chart of the nuclides, some discussion of the Oklo reactor, and you can look it up online. But the Oklo reactor was a natural reactor that operated a few billion years ago. So we can use the dating equations that we just provided to kind of get an idea of what would be a reasonable time for that natural reactor to have been fissioning. This was actually determined when uranium samples from an area were evaluated, and the uranium-235 concentration in those samples was found to be lower than expected. This lower amount of uranium-235 indicated that it had previously fissioned, and they also saw some evidence of some fission products. So it indicated that at one time, the configuration of this natural ore body was sufficient to create natural reactor. And you can read about the details of this. So let's figure out a route of rearranging these equations to determine what was the time that the Oklo reactor was operating. Let's use the amount of uranium-235 as an indicator. Today, 0.7% of uranium is 235. And if we look at a reactor with light water, with regular water, the uranium-235 needs to be at 3.5%. The half-life of uranium-235 is shorter than the half-life of uranium-238. So fundamentally, there's a clock set up that if we know the uranium-235 to 238 isotopic ratio today, and we want the amount of uranium-235 to be 3.5% at time 0. So let's compare the 235 to 238, and we'll call it this uranium ratio, and use our regular decay equation. So we need to just set up the ratios. So the ratio of uranium today is equal to the initial ratio times, we got to take the decay constants for the 235 and the 238, since we're using a ratio of 235 and 238. The time is equal, it's the same. Let's rearrange this equation so that the amount at time 0 is just equal e to the minus lambda 235 times T plus lambda 238 times T. So now we have everything we need to know to solve this equation. We just rearrange, we solve for time. We have the ratio at time T, the initial ratio. We know the decay constants. We rearrange this equation and we get a value on the order of 2 billion years, which is actually pretty accurate. So again, we input the ratio from today, input the ratio that we know that's a condition for the reactor to operate, throw in the constants, calculate, and we get a reasonable value. And all this was done is just based upon understanding that a reactor needs about 3.5% of uranium-235 with natural light water in order for fission to occur.
Based upon the presentations, one should be able to utilize and understand the basic decay equations, relate half-life to lifetime, understand the relationship between count time and uncertainty, utilize equations for mixtures, equilibrium, and branching, understand how isotopes can be used to age an item, and utilize data from sources. One thing I do want to point out for the data from sources is that, again, depending upon the source, you may see different data. An example here for carbon-14, from the chart of the nuclides, the half-life is given as 5,715 years, whereas from the table of the isotopes, the half-life is given as 5,730 years.
So let's review some questions you should be able to answer based upon the lecture. What is the equation that is used to determine the isotope amount at a given time? That's a very fundamental equation, and the basis is shown here, where the n is the number of nuclei at either the initial or at the given time, lambda the decay constant, and then T. This also works for activity or counts or mass. It could work for concentration if the volume doesn't change. What is the equation for the decay constant? This decay constant here, very important term, is log 2 divided by the half-life. One thing you need to make sure is your half-life given in a time unit needs to match the time unit that you would use in this equation. So in this equation here, you have time here in a given unit. The decay constant needs to have that same time unit, obviously from the inverse. What equation is used to find the activity? Again, the decay constant times the number of atoms is equal to activity. This would be counts per whatever the unit is. That's why we often use the decay constant in seconds. So then if I were to do this, I'd get the activity in becquerel, counts per second. And what's the relationship between standard deviation and the number of counts? Well, it's just the square root of the number of counts, and the error is the inverse of that value. Very important term in terms of setting up and performing experiments. Some other questions you should be able to answer. What's the activity of a nanogram of a certain isotope, in this case actinium-225? The main equation to use, activity equals lambda n. So now we need to solve for n for 1 nanogram of actinium-225. We can evaluate that number. We want to get the decay constant for actinium-225. The decay constant's in days, convert that to seconds. Log 2 divided by that, we get a decay constant. Now we plug those values in. Activity equals lambda times n. And a nanogram of actinium-225 is about 1 million becquerel. And that's close to what's used in medical applications of actinium-225, 1 to 10 nanograms. So 7 days later, what's the mass of that actinium? Well, the mass at time t is equal to the mass initial times e to the minus lambda t. We will utilize this equation. The 1 nanogram times e to the minus lambda t is equal to 0.616 nanograms. So 10-day half-life, 7 days later, not quite half of it is decayed. For making actinium, you can use an isotope of thorium, thorium-229, that decays to radium, and then that radium then decays to actinium. So let's ask the question, if I have some thorium-229 and it's decaying, it has an activity of 1,000,000 becquerel, what's the activity of the radium-225 4,000 hours after the thorium-229 has been purified? One starts off with no progeny. The sample contains only thorium-229. It starts decaying, and at 4,000 hours after the purification, it's reached equilibrium. So we see that the radium grows in, and you can determine that at this point, activity of the radium is equal to the activity of the thorium. So it's a parent-daughter relationship. The activity of the radium-225 is equal to the activity of the thorium-229 in a parent-progeny secular equilibrium relationship. And we solved this using the ERG program. We can also define the Curie and Becquerel. A Becquerel being 1 decay per second. A Curie, 3.7 times 10 to the 10th decays per second, where we saw that the definition of the Curie is based upon the activity of 1 gram of radium-226. We also discussed using isotopes in determining the age of objects. What are some of the basic assumptions used for radionuclides in dating? The assumptions are that there are no progeny atoms present at time 0, that all the progeny that are present are due to the decay of the parent, and that no progeny escapes the sample during the time period under investigation. When you have completed this lecture, please comment in the discussion section and respond to the Lecture 3 quiz. The lecture summary, those terms and concepts that you should focus on from the lecture, are shown here. The error in counting is an important term that was discussed, and it's simply the square root of the number of counts. This dictates conditions when one does work with radioactive material. There were a number of examples of utilization of equations of growth and decay. Examples include determining the number of atoms at time t from an initial amount of atoms using this equation, the activity from the number of atoms and the decay constant. This is a very fundamental equation, activity equals lambda n, and the relationship between half-life and the lifetime. This shows that the average lifetime for an atom is a little bit over the half-life. You should be able to calculate parent-progeny relationships. The full equation for the parent-progeny relationship is provided here, where the progeny atoms at a given time are a function of the amount of initial parent and any initial progeny present. Relationships were also presented that can simplify this equation based upon the half-lives of the parent and the progeny. You should be able to do calculations for multiple progeny using programs and understand that the Bateman equation is used to do multiple progeny. However, you will not be asked to develop programs or spreadsheets for doing the Bateman equation. You should understand branching decay, that isotopes can decay by more than one decay route. Often this is not the case, however, there are examples that were presented and that we'll discuss later in the course. You should be able to use the branching ratio for mixed decay to find the partial half-life of a given decay. So for instance, with bismuth-212, which decays by alpha and beta, the data shows a half-life for bismuth-212. You can use that to determine a decay constant for bismuth-212. However, the partial half-lives or the partial decay constants for the alpha decay and the beta decay are based upon the branching ratios. Finally, this lecture discussed age dating using isotopes. You should be able to understand what are the necessary conditions for dating to be successful and what equations can be used for this, particularly the different equations that are used for carbon-14.